In this module, you will learn about the concept of the limit of a function and the condition for a limit of a function to exist. Often, we encounter situations where we wish to find a point or situation where we are interested in a particular outcome. For example, let's consider the sequence shown. We want to find at what point in the sequence we get 1. If we observe carefully, to obtain 1, the sequence needs to be extended infinitely. Here is another classic example. We have an n-sided polygon inscribed in a circle. We have to find for what value of n will the area of the polygon become equal to the area of the circle. Let's start with the 3-sided polygon, the triangle. We can observe that the area of the triangle is not equal to the area of the circle. Next, we will increase the number of sides of the polygon. We increase the number of sides to 12. Still, we can see the distinction between the polygon and the circle. Now, we increase the number of sides of the polygon to 17. We can observe that the area of the polygon is almost equal to the circle, but not actually equal. As we keep on increasing the number of sides of the polygon, the area almost becomes equal to the area of the circle. This idea can be summarized. As n tends to infinity, the area of the polygon equals the area of the circle. This can be mathematically represented as shown. Or concisely as shown. Here, our target is to find when the area of the polygon will become equal to the area of the circle. This happens when the number of the sides of the polygon become infinity. We will extend this understanding of the concept of limit to functions. Suppose we have a function, x squared, which is in fact a parabola. Let's observe the graph of this function. Here, our interest is to find at what point the value of the function reaches a certain value. Here in the graph, we wish to find the value of the function as x approaches any arbitrary point a. The mathematical representation of this idea is represented as shown. As the value of x approaches a, the value of the function approaches L. This is symbolically defined as shown. We read this as limit x tends to a, f of x is equal to L. Now, as an example, we wish to find what value of the function approaches as x approaches 2. We can observe that the value of the function approaches 4. Symbolically, we state this as shown. This means that as x approaches 2, the value of the function approaches 4. Once we have an understanding of the concept of the limit of a function, we can use the concept to analyze functions. To understand this, let's take the function that represents a parabola again. When we talk about x tends to a point A, we can approach A in two ways. We can approach A either from the right-hand side or from the left-hand side. When we find the limit from the left-hand side, we call the limit as the left-hand limit. Similar is the case with the right-hand limit. We represent the right-hand limit and the left-hand limit as shown. The superscripts on the top indicate whether we are finding the right-hand limit or the left-hand limit. For a limit of a function to exist, the left-hand limit should coincide with the right-hand limit. For the function x squared, we will see what the left-hand limit and the right-hand limit are. The left-hand limit is as shown. On the left of the point 2, the value of the function is x squared. The value of the left-hand limit is equal to 4. Similarly, when we find the right-hand limit, we follow the same procedure. On the right of the point 2, the function is x square. The value of the right-hand limit is 4. Thus, the left-hand limit is equal to the right-hand limit. Now we can say that the limit of the function exists and is equal to 4 at x is equal to 2. To understand this concept better, let's see this function. Let's see the graph of the function. Let's evaluate the limit of the function at x equal to 1. For the limit to exist, we have to verify whether the left-hand and the right-hand limits coincide with each other. First, we will calculate the left-hand limit. We took 4x plus 1. Since for x less than or equal to 1, the function is this. The limit of the function is 5. Next, we will find the right-hand limit of this function. If we observe to the right of the point 1, the function takes the form x plus 1. The limit is equal to 2. We can see that the left-hand and the right-hand limits do not coincide with each other. Therefore, the limit of the function does not exist at x is equal to 1. Let's see this graphically. At x equal to 1, the left-hand limit of this function is 5. The right-hand limit of the function is 2. We can see that ambiguity exists. Therefore, the limit of this function at x is equal to 1 does not exist.